Okay, so we are in section 13.8, the divergence theorem. And what we want to do with the divergence theorem is we want to consider finding the flux about a closed surface of a solid. Okay, so up to now, like you learned about flux in section 13.6. And we could, like if we have a surface, we can find the parameterization of that surface and then compute the flux integral. But of course, if we have two separate surfaces that enclose a solid, well, to find the flux through that entire surface, that's the union of those two surfaces, we would have to find the flux through each surface separately and add the flux. Add those flux values? How many recall that from section 13.6? We had a problem like that, right? We had a problem like that. Remember the one with the paraboloid and the disk, and we wanted to find the flux across the surface formed by the paraboloid and the disk, and together they formed the union of those two surfaces made like a surface that enclosed a solid. All right, Ellie remembers that. Well, the divergence theorem allows us to compute the flux. It allows us to compute the flux if the surface we're talking about is a closed surface. So let me show you the theorem. Let me go down here. This is called the divergence theorem. So here we have a simple solid region. Okay, and I like to think of E as just a simple solid. Honestly, when I think region, I think of something in the XY plane. I honestly, think the book should just say simple solid instead of simple solid region. But at any rate, let's say we have a simple solid region, and S is a boundary surface of that solid region E. The surface entirely encloses the solid E. And we're assuming we have positive outward orientation. Well, then let F be a vector field whose component functions have continuous partial derivatives on an open region that contains this solid E. Well, it turns out that the flux across the surface, okay, if I, let me just, the flux across this closed surface, okay, and that flux is going to equal the triple integral over that solid E of the divergence of your vector field. Okay, that's called the divergence theorem. Okay, and they have a proof of it in the book, but we can understand it more intuitively. And I'll talk about that on Monday. Okay, on Monday in class. So this is the divergence theorem. This is the divergence theorem, and I want to look at an example. So I want to go back to that example that we looked at in section 13.6. Do you recall this example where we wanted to find the flux of the vector field across a closed surface S formed by the paraboloid y equals x squared plus z squared, and the disk x squared plus z squared is less than or equal to 1, y equals 1. Okay, so we had done this problem before, and what we did was we computed the flux across the paraboloid surface, and then we computed the flux across that disk. We computed the flux across each of those surfaces separately, and then we added the flux to get the total flux. Well, now we're going to do this problem using the divergence theorem. Okay, let me give you a moment to copy it down, and then we'll go to the solution. Does anybody remember what the flux was equal to for this problem back from section 13.6? If you look in your notes, once you're done copying the example down, look back in your notes in section 13.6, because we did this problem as an example. I remember it. And tell me what the flux was across the closed surface formed by the paraboloid and that disk. That's right, Ellie. The flux was equal to 0. The flux rate, the net flux rate was equal to 0. And as you recall, it took a little bit of effort to find the flux values, because we had for the paraboloid surface, we had to get the parameterization and utilize a surface integral formula, and then for the disk, we had to get the parameterization of a disk and utilize a surface integral formula, right? And so that took a little bit of effort. Well, we can use, and then we added those values. We can use the divergence theorem to help us here very easily. So first of all, I'll go to, here's that solid E. Okay, the solid E is bounded by this closed surface. Okay, there's the paraboloid, and here's the disk. Now, this meets the condition. This meets the condition of the divergence theorem, and of course we're assuming outward orientation. So our flux is being computed with respect to outward orientation. So our normal vectors, our unit normal vectors, point outward. Oh, I got to draw one here too, right? Okay, and of course, every time I draw a solid E, since a triple integral is going to be involved here, I know that after I do the first integral, the second two integrals, I'm going to need a region D to integrate over. Well, the region D, if you take that solid E and compress it in the XC plane, you're going to get a circle. So I just decided right here to draw that circle of radius 1, okay, in the XC plane. And here, x equals r cosine theta. And actually, I should have here not y equals r sine theta, but z equals r sine theta, right? Okay, so, it's just writing things down kind of as I know them. Okay, so the divergence of F, what do we compute for the vector field to get the divergence what do we have to find? What do we have to find for the components of the vector field? What do we have to compute? Well, divergence of a vector field essentially is the net rate of flow at a point in the vector field, right? So we're going to add the partial derivatives. We're going to find the partial derivative of the x component with respect to x, the partial derivative of the y component with respect to y, and the partial derivative of the z component with respect to z. So I'll show that on the next page. When you're ready, let me know. Just give me a thumbs up. All right, Charles is good. All right. Ellie's good. Wonderful. Madeline's good. Excellent. Juliana and Emma are good. Okay. All right. Gordon's good. And then a few other folks here. All right. Well, then, so, all right. Now, keep in mind when we do this problem, this took some effort to do using section 13.6, right? Because we had to compute the flux across both surfaces, the paraboloid and the disk, and then add those flux rates together. Here, with the Stokes theorem, there's no parameterization involved. All we need to do is find the divergence of the vector field F, and then find the limits for our solid E. Okay, so it's like section 12.7 and 12.8, right? Okay, so here we go. Here's our vector field. Here's our vector field, right? And I'm computing the divergence of the vector field. And wow, it turns out the divergence of the vector field is equal to 0. Well, then by Stokes' theorem, okay, I mean, for Stokes' theorem, here, this is the triple integral across the solid E of the divergence of the vector field F dV. Now dV, right, that could be rectangular coordinates, cylindrical coordinates, or spherical coordinates. Okay, but since the integrand equals 0, what's the flux equal to? What's the flux going to equal to? It equals 0. Wow, how easy was that? How easy was that? We had to do some effort, right, in using section 13.6 principles to get that, but we got it. How many are liking the divergence theorem? Okay, Charles likes it. Ellie likes it. Good, and keep in mind, now the divergence theorem works when you have a closed surface, because in order to get a solid, in order to have a solid E, you have to have a closed surface that surrounds that solid E, right? I mean, think of a bowling ball, right? A bowling ball inside of a, like, how many seen like a bowling, well, a bowling, like a bag that encloses a bowling ball? How many have seen that? I don't know if they use those anymore, but like, I think they have them, right? Like bags that hold bowling balls. Has anybody seen that? Okay, Charles has, well, the bag is a closed surface, right? And it encloses that bowling ball. That's the solid. So, you know, so what I do now, just for a little bit of practice, I mean, basically here now we're done. We're done. We have our answer. Type it into WebAssign, you know, we're done. But what I wanted to do just for practice is you know, like section 13.8 is going to give you more practice with triple integrals and finding limits for triple integrals. So if we were to do the dv, right? If we were to do that, okay, and you know, if we go back and look at the solid here, if we look at the solid, okay, based on what you learned in section 12.7, is this solid a, they call it a region. Is it a type 1 solid region, a type 2 solid region, or a type 3 solid region for this solid E here? Is it a type 1, type 2, or type 3 solid region? That's right, Hunu. It's a type 3 solid region. So for type 3 solid regions, okay, when you do your integration, okay, okay, I'll maybe use red here. You're going to go from a surface on the left to a surface on the right. Well, the surface on the left is y equals x squared plus c squared. The surface on the right here would be y equals 1, that vertical plane. Now, it isn't the whole vertical plane because you have a region D, right? But that means then treating this like a type 3 solid region, we're going to get then, if we were to put limits in, the limit on the left would be y equals x squared plus c squared. The limit on the right would be y equals 1. Okay, now then in terms of, you know, dv, right, dv, you still have then, like if you think of dv as dy, dz, dx, then, well, dz, dx, you've taken care of dy here, but dz, dx is dA. Now the question is, do you want to use continue with Cartesian coordinates, or do you want to use polar coordinates? Well, based on that region D from the previous page, based on the region D, which is going to work better, polar coordinates or rectangular coordinates? Based on the region D here. Yeah, it's a circle, right? So you're going to use polar coordinates. There's the circle. You're going to use polar coordinates. So in terms of then the, you know, dA, that's what's left. I'm going to use polar coordinates, and actually I think I have an error here. Hold on, let me check. No, I don't. I don't. Polar coordinates, which is, that came up in section 12.4. The DA is r dr d theta. Now you're still going to get 0, but I'm just trying to show you how you can, I thought it was kind of, how many found this to be a nice little review of finding limits for a solid E, for a triple integral? Was this a nice little, that's all going to equal 0, of course, but yeah, I just thought it was a nice opportunity to discuss that, because finding these limits, I mean, from your exam, right? Finding those limits is half the battle, right? How many would agree? Finding the right limits is half the battle. Who would agree with that? Give me a thumbs up if you agree with that. Okay, Hinu and Ian. Well, it's like the entire battle. Okay, Ian says, yeah, and Gordon and Charles and Ellie. So, so section 13.8 is going to give you some practice here. So are there any questions on this? Okay. So, again now, for the final exam, you have to know what theorem to apply in what situation, right? And on Monday, I think we'll, in our shortened class, I can maybe quiz you a little bit on that. But for now, if there are no questions, I'm going to give you some time to work on the section 13.8 homework. Let me stop the recording.